Alright, so let's take a look at the June 2010 Unit 5 paper. So we've got some molten lead at its melting temperature, and it solidifies. So the temperature of the mold rises from those temperatures, and it's now in thermal equilibrium, so they're the same temperature. So we've got massive lead, specific latent heat of fusion, massive iron mold, specific heat capacity. Calculate the heat energy absorbed by the iron mold. So to calculate that, we know its temperature rise, so we're just going to be using this equation here, the specific heat capacity equation. So the mass of the iron mold is 3, specific heat capacity of the iron is 440, and the change in temperature is 84 minus 27. And if we stick that into our calculator, so 84 minus 27 times 440 times 3 is 7.5 times 10 to the 4 joules. There, giving it two significant figures. Okay, then it wants us to calculate the heat energy given out by the lead while it's changing state. So during the change in state, we essentially have the mass times the latent heat of, in this case, fusion. So it's going to be 1.20 times 2.5 times 10 to the 4. Let's calculate that one. So 1.2 times 2.5 times 10 to the power 4 gives you 3.0 times 10 to the 4 joules in this instance here. So we've got two values there. Let's move on to the next. Calculate the specific heat capacity of lead. So essentially we need to be doing conservation of energy. So the energy from the changing state plus the energy from the lead cooling must be equal to the heat absorbed by the iron. So the cooling energy is going to be, 7.5 times 10 to the 4 minus 3.0 times 10 to the 4 equals, let's just quickly calculate that, so 3 times 440 times by 84 minus 27 is 7.5 times 10 to the 4 minus 3 times 10 to the power 4. So we've got 4.5 times 10 to the 4. We know it ends up in thermal equilibrium, so we can work out its change in temperature. So C is going to be Q over M delta T, which is the 4.5 times 10 to the 4 divided by the mass, which is 1.2, and the change in temperature is going to end up in thermal equilibrium. So we know it ends up at 84 degrees. So let's divide by 1.2 divided by 327 minus 84, which is the change in temperature, gives you 1.5 joules per kilogram per Kelvin using unrounded values. If you use rounded values in the previous one, you end up with 154. So why it's only approximation? Well, for a start, we've assumed all the energy is transferred, so essentially what we've assumed, no heat transferred to the surrounding. Because we've assumed all the energy from the cooling and solidifying substances being transferred to the iron. And also you might say the specific heat capacity assumed to be fixed, and actually typically you find it varies at the temperature as well. So not much, but it does vary with temperature, so again we're assuming it's the constant. Alright, in a thermal nuclear reactor, on a fission reaction typically releases 2 or 3 neutrons. Describe and explain how a constant rate of fission is maintained in a reactor by considering what events or sequence of events may happen to the released neutrons. So the key thing is the different possible things that happen. So the first thing that happens, it will be the neutron, or the neutrons, will collide with a moderator, because that's what the moderator is there for, to be collided with. Moderator, for example, water. And then, so typically what happens is it will have about 50 or so collisions before it becomes a thermal neutron and can cause further fissions. So, so essentially after 50 collisions, and that is an approximation there, obviously it's not always 50, they become thermal neutrons, and that will be a keyword they're looking for, thermal neutrons, and they're probably also looking for a keyword there, moderator. And what can happen? It can cause a fission when absorbed by uranium-235, because that's the fuel essentially in a nuclear reactor. So when absorbed by uranium-235. So those are the things that can happen. It's also, so it's asked you for all the possible events may happen. So what also could happen is the neutron is absorbed by a uranium-238, because that's also present in the reactor. It's in fact majority 238, is only about somewhere between 5 and 10% 235. So another possibility is that they can be absorbed by uranium-238. So that's another possibility of what may happen to it in the nuclear reactor. And then in terms of other things, so if there are excess neutrons, it may be absorbed by control rods. Control rods, because you want an average of 1 neutron emitted per fission reaction, so it can cause 1 subsequent fission. So that's what you're aiming for, so it could be absorbed by one of the control rods to stabilize the reaction there. So that's what's going to be happening there. Alright. Uranium is an alpha emitter. Explain why spent fuel rods present a greater radiation hazard than uranium rods. So, spent rods emit beta and gamma. Which means that they have a higher range, or in the case of gamma, a very long range, and so can damage cells' DNA, because they're able to penetrate through various boundaries that you may have and damage your DNA and damage body tissues and that kind of thing. So to contrast that, whereas alpha has a short range, so it is stopped by even thin shields. So that's contrasting the two. So the spent fuel rods are much more dangerous because they emit beta and gamma, which have a higher range or a longer range and can penetrate through thicker shielding, and they can cause real damage. So alpha is very dangerous, but if you have a very thin shield, even, is enough to stop it doing any damage. Okay, so the age of an ancient boat, so we're going to do some carbon dating, because we've got some carbon-14. What is meant by the decay constant? So the decay constant is essentially the probability of a decay in a certain unit of time. So decay constants have varying units, so essentially it gives you an indication of, in this period of time, how likely is it a decay occurs. Okay, calculate the half-life of carbon-14, giving your answer to appropriate non-significant figures. Okay, so we've got a decay constant of 3.84 times 10 to the minus 12. So half-life is calculated by doing 2 over the decay constant like this, but it wants us, so we'll be able to calculate the half-life in seconds. But it's going to want it in years later on, so it's 3.84 times 10 to the power minus 12. It gives you 1.8 times 10 to the 11 seconds. And so we're going to divide that by the number of seconds in a year. So divide that by 3.15 times 10 to the power 7. Gives you 5.73 times 10 to the 3, because it's 5,000. All the data we've been given is 3 significant figures. So our answer should also, so it'd be 5.73 times 10 to the 3, because it's 5,000. So 3 significant figures. Alright, so next question. Show that the rate of decay of the carbon atoms in the living wood sample is 1.15 becquerels. So the first thing we need to do is calculate the number of nuclei. So that's going to be the total mass divided by this number here. So it's going to give you 3.0 times 10 to the 11 nuclei. So that's the number of nuclei you've got. And you should know that rate of change of that is given by minus the activity times the number of nuclei. So that's going to be what? Oh, it's 3.84 times 10 minus 12. And we're going to multiply that by 3 times 10 to the power of 11. And so if we calculate that, so we've got 3 times 3.84 times 10 to the power of minus 12 times 10 to the power of 11 ends up with 1.152, which is approximately 1.15 becquerel. So the first thing we've done there is we've calculated the number of undecayed nuclei, and then we've used this equation to find the rate of it in this case. Okay, so let's move. A sample of 3 times 10 to the 23 atoms of carbon is removed from a piece of wood taken from the ancient boat. The rate of decay due to the carbon-14 atoms in the sample is 0.65 becquerels. Calculate the age of the ancient boat in years. So what we're essentially going to be using is this equation there. So let's rearrange that a over a0, and we're going to take the log of that. So t is going to be minus 1 over this one log a over a0. So let's put that in. So a is 0.65 because that's what it currently is. A0 was 1.15 because we just calculated it. Log of that times minus 1, and then divide by the activity is 3.84 times 10 to the power of minus 12, and that comes out at 1.485 times 10 to the 11 seconds. So let's divide that by the number of seconds in a year, which is 3.15 times 10 to the power of 7. So that comes out at 716 times 10 to the 3 years. So that's going to be 4.7 times 10 to the 3 years, or like 4,700 effectively. Give 2 reasons why it's difficult to obtain a reliable age of the ancient boat from the carbon dating described. So there's always issues with contamination from other sources, so you may have got some radioactive decays coming from something other than the wood. So that's good. That's always going to be an issue with there. So there is a pretty small sample size used, giving high uncertainty. So if the value of it essentially is small, that's going to give you a high percentage of uncertainty in the result. And then also the carbon dating essentially works from the time the tree stops growing, but the boat have been made as soon as the tree from the wood is cut down. So essentially the carbon dating process all begins at the point when you essentially kill off the plant or stop it producing any more carbon-14. So we're kind of assuming the boat is the same age as the tree, but given the context of the time scale, to be honest, that's not going to have a massive contribution, but it's still valid. Okay. Alright, so let's move on to some thermal physics. Always good fun. So we've got a cylinder with a gas-type piston, and it contains an ideal gas at this temperature, and we've got a pressure, and we've got a volume, and we've got some data there. By plotting 2 or 3 additional points, draw a graph on the axis given to show the relationship between pressure and volume as the piston is slowly pulled out. Slowly changing temperatures means they can be isothermal, so constant temperature. Oh, and we've got temperature remaining constant. So that we know if temperature is constant, that PV is equal to a constant there. So we have to think of some points. So what have we got? So we've got 0.5 times 10 to the power of minus 3 times by 20. So essentially we know the constant is 0.01. So when the volume is 2, so let's take that volume, divided by 2 times 10 to the power of minus 3, we get a value of 5. So we've got this point here. And when the volume is 1, divided by 1 times 10 to the power of minus 3, we know it's going to be 10. So we're going to have that point there. So we've kind of got it halving as we increase 1, like this. Okay, so And then in terms of sketching it, it's going to look something a little bit like this. Hopefully you won't miss the end point like I have up there. So something along the lines of that, and we're just using PV equals constant because temperature is constant in that case. Okay, so let's move on. Calculate the number of gas molecules in the cylinder. So when we're dealing with numbers of molecules, we're eventually going to be using the NKT form of the equation, and we want N, so it's going to be PV over KT. So what values do we have? We have 5 times 10 to the 4 times by 2 times 10 to the minus 3. We're going to dig this number out from the formula sheet. So we've got not Avogadro's number, we've got the Boltzmann constant, which is that one, and we've got a temperature of 290. So let's do some calculations. 5 times 10 to the minus 4 times 2 times 10 to the minus 3 divided by 1.38 times 10 to the power of minus 23, and then divide by 290, isn't it? Yeah. And we end up with a value of 2.49 times 10 to the 22, or giving it its right number of significant figures, it would be 2.5 times 10 to the 22 molecules of gas. We could have used the ideal gas equation to get the number of moles and then multiply by Avogadro's number, but let's get straight into it and get the number of molecules. Calculate the total kinetic energy of the gas molecules. So the internal energy, or the total, is going the number of molecules times the Boltzmann constant times Kt, but divide times by 3 over 2, and you can see where that comes from when you derive it using kinetic theory. So the n is what we've got in the previous one, so 2.5 times 10 to the 22. K is 1.38 times 10 to the power of minus 23. T is 290 times by 3 divided by 2, and that gives you a nice value of 150 joules there. So just using your equation. State 4 assumptions made in the molecular kinetic theory for the model of an ideal gas. So this is a nice reward if you've gone through and learned your gas. So the first assumption you're always making is that the molecules are behaving entirely randomly, or there's a random motion of gas particles, because we extrapolate from the x direction into the xyz by assuming that it is random. We're assuming that gases obey Newtonian equations, so Newtonian equations apply. Obviously things like waves, for instance, don't obey Newtonian physics. You'd expect gas particles to, but it's an assumption we're making. We're always, because we're modelling it statistically, we're always modelling it as if there's a large number of gas particles, because it allows us to use a statistical model. We assume that all the collisions are elastic, because essentially in each collision we're looking at the fact that the momentum going in is equal to the momentum going out. That's part of it. In terms of some other assumptions, we're assuming the size of the molecule is negligible compared to the container, so that the recoil velocity of the container is negligible. We're assuming the collisions are instantaneous. We're assuming all the molecules are the same, so that it's just one gas, it's not a mixture. There's loads of things you could have written there, but those are the ones I'm going to go for. Alright, so that concludes this paper.